from this perspective, it seems natural to define a Berry phase for a given band n as the integral from 0 to 2 pi over a, or from minus pi over a to pi over a, since everything is periodic, of the Berry connection of the cell periodic block states. So that's what people sometimes call the Zeg phase. So up to now, it doesn't look that much different from the Berry phase. So why does it merit a different name? Well, I'm not sure it does. Maybe it does. But there is one difference, which I think becomes particularly clear if we look at the discretized version of the Berry phase. So this is now the Brillouin zone, where the two endpoints are identified. And so I can define my block states along this loop. And in analogy with what we discussed before, the question then becomes, can we evaluate this Berry phase in the one-dimensional Brillouin zone by taking the state? So let me introduce some notation that I forgot, which is so let's say this is j equals 0, 1, 2, 3, 4, 5, so n equals 5. And k equals 0, and k equals 2 pi over a. So I write k so I have a uniform mesh of k points going from one end of the Brillouin zone to the other end. So can we write the following in complete analogy? So this would be correct if the cell periodic block states were identified between the two ends of the Brillouin zone, right? So this would be correct if u at k equals 2 pi over a would be the same as u at k equals 0. But if you remember, the actual condition that we imposed when I first wrote down Bloch's theorem was something like that, but on the size, not on the use. And if you remember that the psi is that the two sets of functions are related by this, then you immediately conclude that this constraint implies for the use a different condition. Okay, and so the logic here was that we wrote on the last overlap u0 because un was the same as u0. So the right prescription is going to be to actually replace un here by this expression on the right-hand side. So the last overlap is going to be different from the previous ones, in the sense that it will contain this exponential in the middle. Okay? So that's the discretized Zeg phase. And you see that there is something funny about it, right? Because it's no longer just an intrinsic property of the set of wave functions, but it also contains the coordinate operator x, right? So there is some spatial information that is embedded in this quantity. It's just not a property of the abstract Hilbert space. So it's something that you just have to live with. So that's the right way of defining a geometrical phase on a one-dimensional Brillouin zone. But it's sort of telling you something, right? It's telling you that this quantity may have some spatial information. It tells you something about the spatial distribution of electrons in a band, okay? And that's actually the case, and you can make this statement much more intuitive by introducing Vannier functions. So that's the next thing I want to do. So the block functions are the eigenstates, and the Vannier functions are just a different representation of the electronic structure of a crystal, which are not energy eigenstates, but nevertheless they are a valid representation because you can go back and forth between one representation and the other without losing any information. So I'll just give the definition. Again, I'll drop band indices, and I'm working in one dimension so that everything is as simple as possible. So the Vannier function is a sort of a Fourier transform of a block function. So for a given band, you take your block states and you do this integral over the entire Brillouin zone of the full block function psi multiplied by this phase factor, which depends on where you are along the one-dimensional Brillouin zone. Okay, and you can do the inverse transformation. So this gives you the Vannier function in terms of all the block functions in a given band, and you can get a block function at a specific k by doing the Fourier, the inverse transformation. Okay. So these are just definitions, which are probably, again, familiar to many of you. And I'll just state very briefly some properties without proof in the interest of time. The first two you can find in any textbook. So you see what's going on here. So the label of a block function is k. And then when you go to the Vannier representation, you integrate over all k. So k disappears as a label. But through this exponential factor, we introduce a new label, which is r. So it's a real space label. So block functions are labeled by a wave vector in the Brillouin zone, and the Vannier functions are labeled by a lattice vector of the real space lattice. So the first property is that the Vannier functions are periodic images. The ones with different values of r are periodic images of one another. So you just need to calculate one, and you obtain the others by translating by the corresponding lattice vector. The second property is that these objects are typically localized in real space if a smooth gauge is chosen for the block functions in k-space. So just from basic Fourier theory, you Fourier transform a smooth function and you get something that is localized. So these are, so the nice thing about Vannier functions is that you sort of recover chemical intuition in a solid where the eigenstates extend over the entire crystal, but by going into this localized representation, you get something that somehow recovers the atomic picture, if you want, or molecular picture. So They are just some functions that are localized on the lattice vectors. X equals plus A, and so forth. Okay. Second property is that they form an orthonormal set. So if you take the scalar product of two Vanni functions with different labels, you get 0, and they are normalized. So if it's the same one, you get 1. So these are textbook properties. And the one I really want to focus on is the third one, which is the centers of the Vanni functions are related to the Z phase. Okay. So the Z phase is a property, a global property of the entire band. And the Vanni function was also obtained by integrating over all K, so it's also a global property, if you want, of the band. And it turns out that if you take the center of mass, and they are localized orbitals, so we can define their center of mass, unlike for the block functions that are extended, so this first moment is not well defined. But for a Vanni function, it is. So I just define it like this. So this is not a cross product now, this is really the position operator. So from property 1, that these are just periodic images of one another, I can write this as the center of mass of the Vanni function at the home cell, R equals 0, plus the R that labels the Vanni function. And the neat property is, which I will again state without proof, that the center of the Vanni function is given in units of the lattice constant by the Z phase over 2 pi. Okay? And, well, of course, we know that the phase is, can be changed by 2 pi, but that then just means that we are shifting the Vanni function by a lattice vector, and that's just relabeling, essentially. So you shift all of them in the same way, so you're just relabeling the Vanni functions. But so what is the physics behind this? So this comes back to what I said before, that the Z phase is special in that the position operator appears. So here it appears again, but in a much more transparent way. So this is actually the first moment of the charge distribution of a Vanni function. Well, yeah, the center, right? So that's the spatial information that is encoded. But so what is the physics behind this? The physics, in the case of an insulator, is very precisely defined. So if you're talking about a valence band of an insulator, and let's say, for simplicity, there is a single valence band. So this gives you, essentially, the collective center of mass of the electrons in the field band. Okay? So it's not a property of any given block state, but it's a global property of the entire field band, and it tells you what is the center of mass in the home cell, in one of the cells, of the electron. So it's an intracell electronic coordinate. And intuitively, you can imagine that if this center of negative charge, so the electrons are negative, so the cell is neutral because you have electrons and protons, and if the center of this negative charge does not coincide with the center of charge of the positive ions, you have a sort of an intracell dipole moment that you can define. And it turns out that this is actually a sharp definition of the electric polarization of an insulating material. So when you have a crystal that breaks inversion symmetry, so typically in 3 dimensions you have like a ferroelectric, barium titanate at low temperature. So these systems break inversion symmetry and you have an electric polarization. And that's actually the proper way of defining it. So the electric polarization, I will call it P, is in 1 dimension is the intracell dipole per unit length. And the dipole is going to be, so let's say that we have one band with spin up and spin down electrons, so we have a factor of 2 to account for spin degeneracy. It's just the difference between the center of the ionic charge inside the cell, so the nuclei in the unit cell, minus the center of the Wannier function in the home cell. Okay, so you have positive charges, you have negative charges. These are real classical charges, the ion charges, and the electrons are delocalized, but I'm basically reducing them to a point charge located at the center of the Wannier functions, and if they don't coincide, then your electric polarization is given by the distance divided by A. So looking at this expression, you can write it, so polarization in 1 dimension has units of charge because the dipole is a charge times distance, and then we divide by distance, so we get a charge. So in units of 2e, it's written as a sum of 2 dimensionless terms. One is the intracell ionic coordinate over A. So let's say this is my unit cell with some lattice constant A. So this would be the tau ionic. So the position of the ionic charge measured from some origin on the unit cell. And this is the Wannier center, x0. So it's 2e times tau ion over A minus Berry phase over 2 pi, so 2-dimensional quantities. So this is the celebrated Berry phase polarization formula that was extremely influential in the electronic structure community. So people working on ferroelectrics were finally able to compute the basic quantity in the description, in the phenomenology of ferroelectrics, which is the polarization. So that was quite a big deal. For a long time, just a few people were excited about it. But I think other people learned that it's actually quite deep. So it turned out to play a very key role in the theory of topological insulators also, these kind of ideas. So I guess I had in mind implicitly a spontaneous polarization in the absence of any external field, which you can have in certain materials like pyroelectrics, ferroelectrics. But the theory has been extended actually to finite electric fields, so you can handle also finite electric fields and compute susceptibilities, linear and nonlinear, applying a similar formalism. But in the simplest application, it's spontaneous polarization. Yes. Okay. So this all looks very intuitive, and I guess it is, but maybe a couple of points should be made, which is the first one, probably the most important one, is that this is not the same as computing the dipole moment of the charge density in the unit cell. That is actually, well, it is well defined in this cartoon picture that I drew where the electrons are really point charges, then that's okay. But in a real quantum mechanical sense, the electronic cloud is delocalized, and this quantity actually depends on the choice of cell that you made. So if you shift your unit cell a little bit, the dipole of the real continuous distribution of electrons with respect to the positive charge of the ions, you can get any value by computing, by choosing a different cell. So, and the reason it's not the same is that when you compute the total charge density at any given point in, let's say, this unit cell here, it has contributions not only from the Wannier function that is nominally centered on this cell, but it also has contributions from the tails of the neighboring Wannier functions. So, so that's one way of seeing that the two quantities are not the same. Okay? And what I'm claiming, again, without proof, is that it's this expression that, is physically meaningful. And the other one way of seeing that it's not meaningful is precisely by repeating the calculation with a different cell, and you'll find that the values you get will just vary continuously. So I did mention that the Berry phase is, of course, only defined modulo 2 pi. So there is something funny still about this polarization that is not unique, because if you recalculate your Berry phase in a different gauge and the value changes by 2 pi, then your polarization changes by 2e or minus 2e. Okay, but that's actually not surprising, not completely surprising, because it already happens at the classical level. So in the Wannier picture, we replace the electronic distribution by point charges. So let's say we have let's say we have a crystal like this. An infinite linear chain. So Wannier center, ionic charge. So the intracell dipole moment, as I defined it in terms of Wannier functions, would be pointing from the negative charge inside the cell to the positive charge. But I might as well place the boundary of my cells in a different way, like this. And if I repeat this motif, I still recover the same chain, right? But now the intracell dipole goes like this, right? And if you compare the two and you divide by the lattice constant A, the difference between these two, the difference between this and this, is precisely E. And then we should put the factor of 2 for spin degeneracy, and that gives us the quantum that I mentioned. So this 2 pi indeterminacy in the Berry phase polarization is perfectly consistent with just a very simple cartoon picture of an infinite chain of point positive and negative charges. So it actually makes complete sense. So there is nothing very mysterious about that from this perspective. Okay. Still, it's a little bit bothersome, because if you talk to an experimentalist, he will tell you that the spontaneous polarization of barium titanate is this, not this modulo quantum. So what's going on there? What's going on there is that if you actually look at how experimentalists measure the spontaneous polarization, what they actually do is that they flip the polarization and they look at the current that flows during this process. So actually what is always measured is a change in polarization. Let's say between the parielectric and ferroelectric phase, or between the two, pointing down and pointing up. So in the end, you always measure changes in polarization. So let's say we recalculate the polarization in a different gauge. And let me call lambda now my parameter, which would be the phonon coordinate that describes the ferroelectric transition. And if I do the calculation in the original gauge, so they will differ by this quantum of polarization. But if I now monitor how the polarization is changing as a function of lambda, then the result is going to be the same with either choice. So I'm now concerned with derivatives of the polarization. And that is independent of the gauge, because they only differ by a constant. When you differentiate with respect to lambda, you get 0. So changes in polarization are completely well defined, and that's what you measure. So the net change in polarization, when you make a finite change in your parameter lambda, like going between the perielectric and the ferroelectric phase, can be computed in any gauge by monitoring the Berry phase and requiring that it changes smoothly without any 2π jump as a function of your lambda. And that's completely well-defined, modulo nothing. And that's actually what you measure. So everything is fine. I will not have time to go through it, but actually at the mathematical level, if you look at the original paper by King, Smith, and Vanderbilt, this expression is actually related to a Berry curvature in a two-parameter space where one of the x's is your one-dimensional k and the second axis is lambda. So now we have a two-dimensional hybrid space, k lambda. You can define a curvature there, and that's related to this. So that's why it's gauge invariant from the mathematical, another way of seeing it from the mathematical point of view. Okay. Any questions about this? So I realize that this, I ask you to assume many things, but I hope that it was reasonable at least. But please ask me questions if it was not. Okay. Then I will come to my last topic, which is the quantum anomaly effect. So this is our first example of a measurable quantity, the electric polarization, that is related to geometric phases in crystals. Right? And the second example I want to give, because I think it's very relevant for subsequent discussions in the lectures, is the quantum anomaly effect. Which is a mouthful, but we'll break it down. So we're now actually back to the more conventional setting of a two-dimensional Brillouin, the one that we've discussed several times. So we have our unit cell in real space AB, and then we have our Brillouin in reciprocal space. And we already know that this is really topologically a torus because of the periodicity of K-space. So this is a two-dimensional closed surface, and there is a Chern number that we can define. So now our Berry curvature, let's say, again, we're talking about the single, let's say we have a system with a single valence band, and I'm computing the Berry curvature for that valence band. So it's defined, it's a scalar defined at every point in the Brillouin zone by this expression that should be familiar by now. And if we integrate this over the Brillouin zone and divide by 2π, we are guaranteed by Chern's theorem to get an integer which is a Chern number. And for most insulators, this is going to be 0. But it turns out that you can come up with toy models and even real materials where it's a non-zero integer. And these are called Chern insulators or quantum anomalous insulators. So the first example at the level of toy models was the famous Haldane model, which is on a honeycomb lattice. But it's actually, once he has done it, then it's easy to come up with many examples. So, and I want to rely on something which is the last thing I discussed in the previous lecture, which was the interpretation of the Chern number on a torus geometry. So remember that? So the Chern number on a torus was given by the winding of the Berry phase along one of the directions. So it's going to be exactly the same thing here. What we're going to do is we're going to split the two-dimensional Brillouin zone into a sequence of one-dimensional strings, let's say along ky, and each of them is a function of kx. And for each kx, I have an effective one-dimensional Brillouin zone where I can define a Zec phase. And the Chern number is going to be the winding of this Zec phase along y, which is labeled by kx as I cycle kx from 0 to 2 pi over a. So if that comes back to itself, the Chern number is 0. If it changes by 2 pi, the Chern number is 1, and so forth. But remembering this equation here, we can think more intuitively of this Zec phase on a given string as a sort of average coordinate along y of the electrons that live on this one-dimensional string of the two-dimensional Brillouin zone. So we have a sort of a hybrid representation where we have a real space coordinate y labeled by kx. Okay? This can be formalized by actually starting from the block functions in 2 dimensions and then doing the Fourier transformation just along one of the directions, along ky. And then you integrate over ky, so you no longer have ky as a label. We've integrated that out. You're still left with kx, but this function is now localized in the vertical direction y, but it's still extended. So it's block-like along x and Fourier-like along y. And its center along y is precisely this Zec phase. So these are sometimes called hybrid Fourier functions. So I'm going to define for each of these strings here a Zec phase along y, which is a function of kx, and it is the integral dk, y, of the Berry connection u dky u. Okay, and then I define the center of this hybrid Fourier function, or this effective average coordinate along y, as a function of kx, just like we did. So just thinking of this as an effective one-dimensional problem where the lattice constant is b. So the coordinate is the lattice the Berry phase over 2 pi in units of the lattice constant. So. And so the winding picture expressed in terms of this coordinate y bar is that if the valence band has a 0 Chern number, then as we scan kx from 0 to 2 pi over a, this coordinate can change, but it comes back to itself. So that's c equals 0. But if it actually changes by a lattice constant b, then which corresponds to a change in the Berry phase by 2 pi, then the Chern number is 1, and so forth. Okay? So, what is the physical property that is associated with this phenomenon? Well, I will just first write the result and then provide an heuristic proof. But it's a type of Hall effect. So let's say we apply an electric field along X, and my claim is that when the Chern number is non-zero, you're going to get a current flowing along Y. And the relation between the induced current and the applied electric field is okay. So the ratio between a two-dimensional current and the field is a conductance. So dimensional, in terms of dimensions, this makes sense because E squared over H is the quantum of conductance. And then the claim is that the prefactor is this integer Chern number C. So to summarize, an insulator, a two-dimensional insulator, can have a Hall response, but then the Hall conductivity must be quantized in units of the quantum of conductance, and the Chern number gives you the actual conductivity in those units. So this is very much like the integer Hall effect, with a very important difference that we don't have any magnetic field here, so we just have an electric field. And that's where the name anomalous comes from, in the sense of spontaneous without magnetic field. So there is only an electric field applied. So this is the quantum anomalous Hall effect. Okay. So I will provide an heuristic justification for this formula. Yes, please.
Let's see. Also, are we missing a 2 from the tendency, or is it containing C?
You're right. So actually, you're absolutely right. So if there was spin degeneracy, there should be a 2. So I guess I'm assuming spinless electrons right now, because I guess so for example, the Haldane model is a spinless model. So, but you're right. Yes. So if you had spin degenerate bands, then you should put a 2. Typically, so in real systems, then you have spin orbit and you break time reversal. So actually, the bands split. You don't have spin degeneracy, but anyway, let's assume spinless electrons. So the way to justify this equation in simple terms is to remember from the semi-classical equations of motion that if you apply, for wave packets in crystals, if you apply an electric field, you change the crystal momentum. Okay, so let's say that we apply an electric field along X, like in this cartoon, the wave vector Kx is going to be changing. So in this hybrid representation, you sort of see now what's happening, because your electrons so this is a hybrid space, real space Y, reciprocal space X. You apply the electric field along X, and the electrons are moving in this axis, like so, but then their vertical coordinate Y is changing, okay? And after one block oscillation, so after the time that it takes to go from one side of the Brownian zone to the other, the Y coordinate has changed by a lattice constant. And we can do the numbers, so you'll see that you get precisely that coefficient if you plug in the numbers, so we can do it quickly. So we want to consider what happens after a change. So let's say the electric field is applied in the positive X direction. So there is a minus sign here. So my E is positive, is the elementary charge. So K is changing in the negative direction. So the the Brillouin zone, the delta kx over the full Brillouin zone is minus 2 pi over a. So and it takes a certain time, which is the block oscillation time delta t. And delta t is h bar E a electric field x. And over this time, the y coordinate has changed. So now you have to be careful with the signs. So the electric field is along x. The electrons are moving in this direction. So if the Chern number is 1, the coordinate changed by minus b. So we started here and we went down. So if the Chern number is c, it changed by minus cb. Okay? So the average velocity that you can construct out of this for the electrons is the net change in coordinate over a block period over that time delta t. And what you get is minus c eh ab ex. So that's a... Yeah. Yes, absolutely. Yes. So now I want to go from a velocity to a current, so I need to multiply by a charge density. So I have, so again, spinous electron. So I have one electron minus E, charge minus E, over a unit cell of area, A times B. And I multiply this by the average velocity during this oscillation, the velocity induced by the electric field. And what I get is precisely plus C E squared over H Ex, which is what I claimed somewhere here. Okay? So, so in this case, the external parameter that is changed in K is the electric field, and you can worry about how good the adiabatic approximation is. So that was a question that came up at the very first lecture that I gave. But if you look at this equation, then you don't worry so much, because the rate of change of K is proportional to the electric field. And we are basically doing linear response here, right? So we want a current induced at first order in the field, so we can make the field as small as we want. So as far as linear response is concerned, we can make the electric field as small as we want, and then the rate of change of K is small. And then there is the adiabatic approximation works well, because this is an insulator, there is a gap. So we can always approach the regime where this approximation holds. Okay. So this quantity here is our Hall conductivity. And if we remember this expression for the Chern number, then we can write formally this anomalous Hall conductivity for an insulator. So which I defined as Jy over Ex as E squared. There is a 2 pi here, so 2 pi H, and then the integral over the Brillouin zone of the Berry curvature. So the polarization gave us an example of a physical observable associated with the Berry phase. And the quantum anomalous effect in two-dimensional insulators is an example of an observable associated with the Chern number, which in turn is expressible as the Berry curvature. Okay? The very last thing, so how much time do I have? Okay, so I will finish before. So the very last thing I want to mention, to come full circle, is what happens if, so here I have some valence band, some conduction band, there is a gap, and the Fermi level lies somewhere here. So this is the Chern number of my valence band, let's say it's +1. So, and now I want to ask the question, what happens if now my band is, let's say, half filled, so the Fermi level cuts through the band. So I no longer have an insulator, but I have a metal. What's going to happen to this anomalous Hall conductivity? So, so now what I want to do is to introduce an occupation number, so the Fermi occupation. So at t equals 0 is just 0 and 1, and it drops sharply at the Fermi surface. So this is the occupied region of the Brillouin zone, and this is the empty region. And so for the insulator, the entire Brillouin zone was occupied, and you obtain the Hall conductivity by integrating the curvature over the entire Brillouin zone. So what we're going to do for a metal is do the same, but we just restrict the integral over the occupied region. Okay? So now, occupied region of the Brillouin zone. Okay? So I think it looks quite plausible. But so, well, what can we do here? We can apply our favorite trick, which is Stokes' theorem. Right? So the curvature is the curl of the connection. We're integrating the curvature over this region enclosed by a boundary, one-dimensional boundary. So the integral of the curvature over the surface enclosed by this boundary is equal to the integral of the connection around the boundary. Okay? So we get this beautiful result, which is that the anomalous Hall conductivity of a metal is given in units of the quantum of conductance E squared over h by the Berry phase over 2 pi. And what is the contour of integration? Is the Fermi surface, which, okay, since we are in 2 dimensions, it's not a surface, it's a loop. Okay? One subtlety is that for the insulator, the formula gave us the anomalous Hall conductivity precisely. For a metal, if you apply this formula here, in terms of the Berry phase is only defined modulo 2 pi, so this gives you the anomalous Hall conductivity, which is can be whatever. So if you shrink the Fermi surface, this number will change continuously, but it gives you the right answer only modulo E squared over h, because the Berry phase is only defined modulo 2 pi. So the Fermi surface formula for the anomalous Hall conductivity gives you the non-quantized part, if you want, of the anomalous Hall conductivity. Okay? So, yeah, so I think this is a good place where to end, because there it is, a physical observable associated with the Berry phase on a loop in the two-dimensional Brillouin zone. So, yeah. So actually that's all I had to say. Let me just, to conclude, to tell you where you can get the notes. So I posted them on a link on my webpage. So this is all lowercase, but I'll write the URL in uppercase so that it becomes more readable. So cfm.ehu. Maybe if someone has a computer, you can check that I'm doing it right. That es / my first name, Ivo, / lectures, not PDF. So that should give you the full set of notes. So, are there any questions about this? Yes.
If we have multiple buckets on the Fermi surface, arbitrarily some are electron-like, some are hole-like, do we just do this process one bucket at a time and then
Add up, yeah. You have to be careful with the holes. You should do the circulation in the opposite direction, but yes, that's right. You can also, so this is for two-dimensional systems, and of course, the anomalous cell conductivity has been measured mostly in bulk metals, three-dimensional metals. So this can all be generalized to 3 dimensions, and you can actually do this. Actually, one way of doing it is you take the 3-dimensional bryosone, you slice it into 2-dimensional slices, and on each of those, the intersection of the slice with the 2-dimensional Fermi surface is 1-dimensional loops. And then you do the Berry phases on those loops, and you add up the results from all the slices, and you get the 3-dimensional anomalous cell conductivity. Yes. Yes.
So in a matter when you Fermi level extend, don't these quantum unit get washed out by the usual anomalous cell conductivity coming from say scattering or impurities, skew scattering, or the intrinsic side jump whenever you have to get
Right.
washed out.
Well, so that was the whole discussion on the literature on the anomalous cell conductivity. So this, you're right, so this is not the full story. So this is what's called the intrinsic anomalous cell conductivity in the sense that it's called intrinsic because it's a property of the pristine band structure and there is no scattering time here. And then there are some other contributions associated with scattering from impurities. Skew scattering, the conductivity contains the scattering time, and then there is this side jump, which is quite mysterious, which also does not depend on tau, even though it is extrinsic. So there was a whole discussion over many decades, actually. And I think it was, to a big extent, thanks to the ab initio calculations of this intrinsic contribution to simple ferromagnetic metals like iron, cobalt, and nickel, that established that the numbers you get out from that can be actually very close to the experimental result, at least in the dirty limit. So there are regimes where this contribution is actually important. So it's clear by now that, so the story is complicated, you're right, but it's clear that this contribution can be important in many situations.
And that is not quantized. I mean, it's arbitrary. It's defined at the full time.
Well, there is a unique answer. If you calculate it as a Fermi surface property, there is this quantum of indeterminacy, but if you integrate the Berry curvature over the Fermi C, you get a unique answer for this intrinsic contribution. It's not quantized, you're right, but that's what you should compare with the experiment. Yeah. Right.
For an insulator, you know the sigma x y completely. So if you go just a little bit, then do you know the entire value or modulo of sigma x y?
You can know the entire value by doing the Fermi C calculation in terms of the curvature. Yes, the entire value of the intrinsic contribution. Not just modulo 2 pi, yes. So if you use this expression, so this expression gives you the result modulo nothing. It's this one, it's when you go from here to there that you introduce the quantum of indeterminacy because you went from a curvature, which is gauge invariant, to a phase. Yeah, it's a little bit mysterious, right? Because this is a DC transport coefficient, and you would expect it to be a Fermi surface property from the Landau Fermi liquid theory. And it looks like, at least in terms of the bulk Fermi surface, you can only get it modulo quantum. This is something that Haldane has, I think, thought a lot about. And I think he had some ideas that maybe looking at the Fermi arcs, you could resolve the quantum. But okay, we are getting on deep waters. That's correct, yes. So, yeah. Right, so if you do like for the Haldane model, if you imagine scanning the result of this computation, let's say sigma normal sol in unit of e square over h, so it will go up and then it will plateau at the quantized value when you're, so as a function of the chemical potential, as you said. So as you're cutting through the band, it goes up and then it plateaus at e square over h. That's right. Yes, right. If you have a valence band with a zero Chern number, but that does break time reversal symmetry, like at certain portions of the phase diagram of the Haldane model, what you're going to get instead is that as the chemical potential cuts through the band, the anomalous cell conductivity becomes non-zero, but as you approach the gap, it goes back to zero. So in that case, in the insulating limit, you get zero for the anomalous cell conductivity. Yeah. Did anyone check the URL? Does it work? Okay.